If we separate the oxidation from the reduction, it allows us to harness the flow of electrons to produce electricity. And so if we keep these separate, they're called half cells. And we can remember which one is which by a mnemonic device, an, ox, and red cat. And what that stands for is the anode is where our oxidation occurs, and the cathode is where the reduction occurs. And this is just an easy way to keep and remember these. We do have to include something called a salt bridge. So you'll notice between the two solutions there is what we call a U-tube, a tube that's in the shape of a U, and this is filled with an electrolyte solution. So remember, electrolytes allow the flow of charge, and this helps to keep the charge from building up and allows the flow of the current to be complete. We do have a shorthand notation that we use in order to represent the electrochemical cell. The oxidation half cell is always on the left, the reduction half cell is always on the right, and we separate those two cells by two vertical lines. Now, we always start with the electrode or the solid part of our cell. So in the previous example, the electrode was zinc. For the oxidation, we would use a straight line to represent the transition between the zinc metal and the zinc solution. And this is usually followed by a concentration, or you might see it followed by a concentration. We then use a double line to represent the salt bridge. And then we put the electrolyte solution from the cathode. So in our previous example, it was copper 2+. We put a straight line to represent the phase transition from the solution to our metal electrode, which in this case was copper. So here's another example. So this is a different electrochemical cell where our anode, which is the negative part, the electrons are flowing away from the anode. It starts out as the iron. We have it's in an iron 2+ solution. We've got a double line representing our salt bridge. And now we have a different case that we didn't see previously, where our reduction is actually happening in solution. So the manganese O4- is actually being reduced to Mn2+, and this happens in acidic solution. And so all of these species, all of these ions are represented by commas that separate them. The cathode in this case is platinum, and so our platinum electrode, we have the solid line representing the phase transition, and then the platinum electrode. And frequently, platinum is used because it is not reactive, and it also conducts electricity very well. If we're dealing with very acidic solutions, platinum will not dissolve. This is an example electrochemical cell for you to try writing cell notation for. Please pause the video and write the cell notation. The anode is always placed on the left-hand side of our cell notation. The way that we tell which one is the anode is that it is the negative side of the cell. So because this is marked negative, this is going to be our anode. Another way to tell is that when we are recording a positive value, the black colored lead is attached to the anode of your cell. So we're going to start by writing the solid electrode, followed by a straight line representing our phase transition from the solid into the solution. And the part of the cell that is taking part in our electrochemical cell is the tin 2+ in the solution. This is followed by our double line representing the salt bridge, which is shown in yellow. And then we move to the cathode side, and we start with the solution, which in this case is the copper 2+. We put the solid line representing the phase transition to the cathode of the cell. Now, if we want to actually measure voltages, we have to have a 0 point to measure against, because everything is relative, because we're measuring the transfer of electrons. And so chemists have decided that as a standard half reaction, they're going to use the reduction of H+ to hydrogen under standard conditions to be our 0 point to measure everything else against. So we can set up a standard hydrogen electrode, which is abbreviated SHE. It uses a platinum electrode, inside of which there is hydrogen gas at 1 atmosphere that is bubbled through an acidic 1 molar solution. And so this is our standard half reaction against which all other potentials are measured. To measure the electrochemical potential, we hook up a voltmeter into the circuit that contains our electrochemical cell. Sometimes you'll see a voltmeter represented as a circle with a V in it. You'll notice that our hydrogen half reaction or half cell is the cathode. We know that it's because it's positive, and it's also hooked to the red part of our voltmeter. Our anode is zinc. And so when we measure the zinc half reaction compared to hydrogen, the voltage that we're getting is 0.76 volts. And so we can do this with lots of different metals to determine what our half cell and what those potentials are for different metals. So our SHE, or standard hydrogen electrode, is defined to be an exactly 0 for our potential. Now everything else that is listed is comparing the tendency for these reactions to occur relative to the reduction of our hydrogen electrode under standard conditions. So if half reactions have a stronger tendency towards reduction, they have a positive value for the E. If they have a stronger tendency towards oxidation, then they have a negative value for our the electrode potentials. And so we can decide based on this list which ones are more likely to be the anode or which ones are more likely to be the cathode. The anode, because it prefers oxidation, is going to have the more negative value on the table, and the cathode is going to have the more positive value on the table. If we want to calculate what our standard cell potential is under standard conditions, we need to compare our reduction potentials to each other. And it's going to be the reduction potential of the element that is being reduced minus the reduction potential of the element that is being oxidized. And the reason that we have the negative sign in there is because the oxidation reaction has to be reversed from what we measured in our table. Another way to think about this is it is equal to the potential of the cathode minus the potential of the anode, because the cathode is where the reduction happens, the anode is where our oxidation happens. Now, something that is a little different than some of the other properties that we've looked at is that when we add those potentials together for the half cells, or subtract them because we have to reverse the reaction, we do not multiply the half cell potentials. Even if we multiply the reaction to get our electrons to balance, the half cell values are standardized, and so we do not multiply those values. This is why large batteries give you the same voltages as small batteries. So if you have a 1.5 volt AA, it is the same voltage, 1.5 volts, as a AAA because it is not an extensive property. Substances listed at the top of the table are more likely to undergo reduction. They're good oxidizing agents, and because they're more likely to be reduced, that means that those are more likely to be the cathode. Substances listed near the bottom of the table tend to undergo oxidation. They are better reducing agents. That means that they are more likely to be the anode. So the more negative the value is, it is going to be the anode. And if we have a spontaneous reaction, the more negative value is the anode. The more positive value is going to be our cathode. And the reaction is going to want to go in that direction. So our spontaneous reaction is going to be the zinc forming zinc 2+, the copper 2+ forming copper. The other reaction can happen, but we have to apply an external electrical current. So what this means is that if we calculate our Ecell, if that has a positive value, it is a spontaneous reaction. If it has a negative value, then it is non-spontaneous. Here we have a chemical reaction, and we want to determine if it is spontaneous. So we have aluminum that is going from an oxidation state of 0 to +3. And so this is oxidized because oxidation is loss of electrons. And because our aluminum is being oxidized, that means it is the anode in our chemical reaction. If we look at our value, it is negative, which means that it is more likely to be the anode. If we calculate our Ecell, it is cathode minus the anode. In this case, it is a positive 0.96 volts minus a negative 1.66 volts. That gives us a positive 2.62 volts. Because it is a positive value, that means that this is a spontaneous reaction with aluminum acting as our anode. Determine the Ecell for this chemical reaction and see if it is spontaneous. So take a minute, pause the video, try this problem for yourself. So let's look at one of our compounds. So the I minus is a negative 1. It is going to I2, which has an oxidation state of 0. We're going from a negative 1 to a 0. So this is a loss of electrons, which makes this the oxidation. Oxidation is the anode, which is our more negative value, which is true in this case, meaning that this should be a spontaneous reaction because our oxidation is also the more negative value. Let's calculate our Ecell. So we're going to take the potential of the cathode minus the potential of the anode. Cathode is our more positive value minus a positive 0.54 volts. And so we end up with an overall cell potential of positive 0.66 volts. Because this is a positive value, that means that this will be a spontaneous reaction. So it would be a Voltaic cell.